We're going to continue our study of kind of an introduction to proofs here by exploring the concept of implications. We already saw this idea in the previous section and some previous videos, but we're going to be looking at it in more detail here. So, we say here that the most important type of a statement in mathematics is the implication, and we're going to try and convince you of that, right? So it's also the least intuitive of our basic molecular statement types. So our goal in this section is to become more familiar with this concept. Some examples of mathematical implications, again, some really famous theorems, the Pythagorean theorem, for example. If a triangle is a right triangle with leg lengths a and b and hypotenuse length c, then a squared plus b squared equals c squared. Something about even integers. If an integer is divisible by 4, then it is even. And something from calculus about differentiability. If a function is differentiable, then it is continuous. Most mathematical theorems are implications. So all of these are implications, as are most mathematical theorems. So a really important structure for us to be comfortable with. Math is about making general claims. However, mathematical statements are rarely true for every object. Implications allow us to restrict our attention to the objects we care about. So the general structure of an implication is if a mathematical object has the right properties, then a conclusion follows. And just to remind you of our definition of an implication is a statement of the form if P, then Q, where P and Q are statements. So P is what we call the hypothesis or antecedent, and Q is the conclusion or consequent. And again, something we went over in a previous video, but to remind you here, the truth of an implication. So the implication, if P then Q, is false only when P is true and Q is false, and it is true in every other case. So if P is false, then we don't actually care what the truth value of Q is. This statement as a whole is true, which is a little bit strange. But if P is true and Q is true, then this is true. So the only situation we are kind of worried about this statement not being true is if P is true and Q is false. Why does this make sense? Consider a statement, an example here. If a student studies hard, then they will pass the exam. When would we consider this statement false? I.e., if I made this statement, in what circumstances would it be fair to call me a liar? That would only be if the student studied hard and did not pass. That would be the only situation where you could make the claim that this statement is false. If a student doesn't study hard, then it doesn't really matter whether they pass the exam or not. This, the truth of this statement is not something that you could refute. And if a student studied hard and they pass, then this is true. So the only time this wouldn't be true, when you could call me a liar, is if a student studied hard and did not pass. Right? So again, if the student never studied hard, the implication did not make any promise about what would happen. Although we often read, P implies Q, or if P then Q, this does not necessarily mean there is a causal relationship. So for example, here's a implication, if 2 plus 2 equals 4, then Baltimore is in Maryland. Both parts are true, so the implication itself is true. However, the first statement clearly does not cause the second. There's no causal relationship there. Baltimore is in Maryland, and 2 plus 2 is 4, but there's nothing about the fact that 2 plus 2 equals 4 that is leading to this idea that Baltimore is in Maryland. Let's try a few examples here. So we want to determine whether each implication is true or false. Again, if P then Q is false, precisely when P is true and Q is false. So we're looking for statements that would be of that form in order to have the full implication be false. Otherwise, it should be true. So first one here, if a square matrix has determinant 5, then it is invertible. This first part, the P part, sort of, I guess, depends on your particular matrix. So that might be false. You might have, a matrix where the determinant is 5. And if you haven't studied determinants of matrices yet, you will at some point in your linear algebra class. But that is a quantity we can assign to a square matrix. So what we care about here is the situation where that is true. So let's suppose we had a square matrix with determinant 5. Then would it be invertible? It turns out that yes, it would be. So if P is true, then Q is true. And so this statement as a whole is true because both parts are true sort of together. They are also false together, but that doesn't actually matter here. What about this one? If 2 is odd, then 5 squared equals 25. Here we have that, P is false. 2 is not odd. So, the whole statement, if P then Q, is automatically true, right? We don't actually care about the whether the Q portion is true or false. So, 5 squared does happen to be 25, but we don't care. The hypothesis here is false, so the statement as a whole is true. What about this one? If 2 is even, then 5 squared is equal to 20. Here, P is true and Q is false. So the statement as a whole, if P then Q, is false. And this makes a lot of sense. If this were a true statement, we'd be in trouble, right? Because 2 is even and 5 squared does not equal 20. So if I were to say, well, the statement, if 2 is even, then 5 squared equals 20 is a true statement, then, something would be off there. I guess 5 squared couldn't equal 20 or would have to equal 20 because, 2 is even. So this statement as a whole is false. If two distinct lines in the plane are parallel, then they intersect. Again, this sort of depends on the lines we're looking at. Let's suppose we had parallel lines in the plane, they would not intersect. And so we have a situation where if the first part is true, then the second part is false. So this statement as a whole, this if P then Q, is false because we have the possibility where, if this were true, if two lines in the plane were parallel, then they would not intersect. That's sort of our definition of parallel lines, or one of our definitions of parallel lines. If a vector belongs to R3, then it has 3 components. Again, sort of depending on the particular vector. If our vector does belong to R3, then it would have 3 components. If it doesn't, if the first part is false, then the second part would be false. But the main thing we're looking at is assuming that first part is true, the second part would be true. So the statement as a whole is true. So just to review, the first one here was true. The second one was true. The third one was false. And the fourth one was false. So overall, true, true, false, false, true.